Yeah. Okay, so today I'll be talking about how to search for dark matter using MeVCube, and this is based on something that I've been working on for some time. Okay, this slide has been shown many times, but let's again say that. So the idea being, if we just ask the question that what is the universe made up of? So if we just look at the energy content, then the ordinary matter, the things that you and me are made up of, is just like 5%, and it is actually dominated by dark energy and then dark matter. And today we are interested in this chunk of 26.6%, that is dark matter, right? Now there are many evidences for the existence of dark matter. We know that dark matter is there, that's why I'm giving the talk. And so some of the examples are galaxy rotation curve, bullet cluster, cosmic microwave background. But I'll not go into the details of any of these evidences. But all these evidences tell us is that dark matter interacts with gravity, right? So dark matter has some mass. But we don't know if there is some non-gravitational interaction by which dark matter talks to standard particles, or even dark matter talks to itself, right? And because we don't know that, the possible mass range of interest for dark matter is actually huge. So you can see that here. So it starts from 10 to the minus 21 electron volt, goes up to some solar masses, right? So dark matter can be a particle of mass 10 to the minus 121 electron volts. Dark matter can even be a black hole of 10 to the 3 solar mass, right? It's a 90 orders of magnitude. And the smart thing to do here is that make use of all the data that we have, or all the observables that we have, right? Okay, so because we have a vast sort of mass range to probe, there are various different ways that people try to search for dark matter. And broadly they can be classified into these 4 parts. The first one being the indirect detection, second one is the direct detection, then we have collided search, and last but not the least the astrophysical search, right? Now again, due to the time constraints, I will not go into the details of all of this, but I'll rather focus on the first one, that is the indirect detection. Okay, so the question is, what is indirect detection of dark matter? So this right here is a very simple Feynman diagram where time is flowing from left to right. And what this diagram is telling you is that 2 chi particles, which are dark matter particles, can annihilate and produce 2 standard particles, right? And this is the basic philosophy of indirect detection. So the idea being that you cannot individually detect these dark matter particles, but if dark matter particles annihilate or decay to produce some standard particles, we actually know how to detect standard particles, right? So the strategy is that you take your telescope, you point your telescope to the regions of sky where dark matter density is high, and you expect to see some excess of the standard particles that are coming from dark matter, right? And obviously one of the standard particles we know is photon. So it can happen that dark matter can annihilate or decay to give some photons, and we can try to detect it. So now let's review how good we can see photons, right? And obviously we can do better than just looking by your eyes, right? So this shows you the progress that we have made in the last like 50 or more years. So this right here are the different wavelengths of photon from gamma ray to radio. And these are the corresponding telescopes, both ground-based and space-based, that are right now operating, right? So for example, this right here is the Fermi-LAT, which is operating in the gamma ray, right? And these are not the only satellites, there are many, many more satellites that are out there, right? And if we want to look at this picture in terms of sensitivity, then this is the picture, where in the x-axis what I have is the energy of the photon, in the y-axis I have the sensitivity. And sensitivity, you can think of it like the least amount of flux that you can detect, right? So the less this number, the better your telescope is. And here you can see the sort of sensitivities from various telescopes. For example, this is from this Fermi-LAT, this is from the Chandra, and many more, right? Now a weird thing that you'll notice in this picture is that suddenly in this gray band region, the sensitivity achieved is actually very bad, right? By this COMTEL. So the sensitivity achieved by COMTEL is much worse compared to Fermi-LAT and Chandra, right? And this is something known as the MEV gap. So MEV gap is a gap in the energy range of photon where the sensitivity achieved by us is much worse than compared to any wavelength or energy. And there are many reasons why there is a MEV gap. And so one of the main reasons is that after the decommissioning of this COMTEL telescope in 2000, there has not been any major mission or telescope just focused in this region of energy. And hopefully that will soon change, because there are many proposed satellites that will try to target this MEV gap. So on the left, this is the COSI mission, this is the e-astrogram, this is the GECKO, and this Amigo X. These are all proposed satellites that will try to detect photons in this MEV gap. And interestingly, recently this COSI got green light. So COSI mission will be launched in 2027 by this SpaceX, right? So this is going to revolutionize the MEV sort of astronomy and astrophysics. Now, one simple question that you can ask is that, okay, we have a gap in the energy range where the sensitivity is very bad, and we have so many missions that are sort of proposed, so why not just launch all these telescopes in the sky, right? Then we can sort of detect the photons much better way in that MEV gap, right? Now, the reason why we can't do that is basically a practical reason, that is due to the money constraint, because these experiments are large-scale experiments and they take a lot of money to build. So, for example, the last big experiment to be launched was JWST. The cost was around $10 billion. So, these experiments actually cost a lot of money, and also the development and sanctioning all these things take around 8 to 10 years, right? These are long-term projects. So that is the reason why an alternative trend is coming up in astrophysics and astronomy, and that is the trend of this CubeSat technology, right? So what is the CubeSat technology? So the CubeSats are these small mini satellites that have capabilities just like any big satellite, right? So everything is integrated in a small space, and a standard CubeSat is 1 unit, and this is comparable to the size of a Rubik's Cube, right? So you can imagine how small this telescope is, right? And obviously, if you want a bigger sort of effective area, you can stack this 1 unit up to like 12 unit or 24 units. And because this is small scale, the weight of this thing is also very, very less. And the weight is actually a determining factor when you want to launch a satellite. So for example, the COSI mission will sort of, just the launching cost is like $69 million. And right now, SpaceX has a like Uber pool service where they launch CubeSats. It costs $275,000 to launch a 50 kg CubeSat, which is a sort of maximum weight you can have. So then looking at this figure, you can think, okay, this is a very upcoming technology that is very useful. But actually, right now, there are over 4,000 CubeSats that are in space, right? And here, there are some examples of some of the CubeSats that come under the umbrella of ESA. And all these CubeSats are right now operating. And most of them are being used for, let's say, atmospheric science and weather forecasting. So now, given the problem that we have in our hands, that we have a gap in the energy range where the sensitivity is very bad, you can ask a simple question that, okay, I understand that I cannot launch big missions in this energy range because it will take a lot of money, but why not launch these small satellites, right? Because they will take a less amount of money, the development time is less, and also if they go bad, you don't get sad because you have not invested $10 billion, right? So why not use a CubeSat technology MEV telescope? And actually recently there has been a proposal by a DESI group where they have said that they can make a CubeSat standard MEV telescope, and the name of the telescope is MeVCube. So how does MeVCube work? So this is basically the way MeVCube detects photons. So MeVCube has two sort of layers of cadmium zinc telluride material, and a photon from a source can come in, Compton scatter in the first layer, and the scattered photon can get absorbed in the second layer. And by detecting this absorbed photon and this electron, it can reconstruct the energy and the direction of the photon, right? And the energy range of interest for this telescope is said to be 200 keV to around 4 MeV, right? So given the specifications, one can sort of calculate the sensitivity of the telescope. And this is the plot where in the x-axis I have the energy of the photon again. In the y-axis basically the sensitivity. This black solid line is from the COMTEL mission that was decommissioned in 2000. And you can see this blue solid and the dotted lines are for the MeVCube. We don't know what size will be launched, so you can test for various sizes. But you can see that with MeVCube, you can reach lower energies of the photons, and also the sensitivities are better, right? And just one reminder is that the size or the sort of the mass of the COMTEL was 17 ton. This will be around 20 kgs, right? You can imagine how small scale this is. And even with that, you can achieve comparable sort of sensitivity with COMTEL. And there are many science goals for this MeVCube. So it will try to detect GRBs, it will try to detect emissions from this aluminum and iron decays, then it will try to sort of solve this galactic 511 kV excess, also multi-messenger astronomy. So these are sort of the targets for all different MEV satellites in this energy range. But what I am interested in here is that given the small size of the detector, can it do or can it search for dark matter, right? And to know that, what I have to first start with is that I have to start with the dark matter candidate. So already I have shown you that there are many candidates depending on the mass of dark matter. So the first candidate I will take is the heaviest candidate, and the name of the candidate is primordial black hole. So the first question is, what is a primordial black hole? So as the name tells you that it's a black hole, but whereas astrophysical black holes are coming from star collapse, these black holes are formed at a very early stage of the universe due to collapse of density fluctuations. But after you form these guys, they act just like any other black hole. So if you know the mass of these black holes and you know the spin, you can determine the temperature, and depending on this temperature, they will Hawking evaporate. And the spectra of this emission can be given by this, where gamma is the gray body factor, and this E dash is the total energy of the particles, taking into account the rotation velocity of black hole. So the physical picture here is that these primordial black holes are dark matter candidate. They are evaporating, producing different particles, right? So they are producing E plus E minus neutrinos, photons. And what I want to check is that can this MeVCube detect these photons, right? And so first what I have to see is that what is the flux of photon that is coming from this candidate, right? And that I'm showing here, where in the x-axis I have the energy of the photon, in the y-axis I have the flux, and this plot is done for a primordial black hole of mass 10 to the 17 gram or 10 to the minus 16 solar mass, so they are really tiny. And the fraction of dark matter that it makes up is around 10%, right? And with that, if you look at the center of our galaxy, then this red solid line and the violet solid line are the sort of total flux of photon expected from primordial black holes, right? So this is the signal that I'm after. But just like any other searches, there are backgrounds, and these backgrounds are mainly being contributed by diffuse emission and also some unresolved point sources. And this is the total background. This green line is the total background expected. So now I have a flux from my PBH, or the dark matter candidate. With the given sensitivity of MeVCube, I can try to test that can it discover PBH dark matter. And so this is the result, where in the x-axis I have the mass of the primordial black hole in gram. I don't know the mass of the candidate. In the y-axis I have the FPBH, which tells me what fraction of dark matter is made up of PBH. So FPBH1 means all dark matter is primordial black hole. And for example, these dotted lines that you see, these are previous limits on the parameter space, and these are coming from various different telescopes and various different observables. So now what I'm showing is that if I sort of use the sensitivity of MeVCube, what is the reach of the telescope? And the reaches are shown by these red, blue and green curves. These are from 2 units, 6 units and 12 units. So the bigger the size, the better it is always. And what is showing is that in future, if it gets launched, then it can probe new regions of parameter space, right? So what that means for dark matter can be shown here. So this is the scenario right now, that these are all the constants that we have in the parameter space. And let's say dark matter really is somewhere here, right? What you see here is that this dark matter is beyond the capacity of present limits, right? So if dark matter is here, I cannot say anything. I have not seen it. But with the launch of MeVCube, you see that it can reach these regions, right? So if dark matter is really here, MeVCube will be able to discover it, right? So this is a very strong limit that will come for primordial black hole dark matter. Now this is very nice for primordial black hole, but can other candidate also work? And another candidate that can work is sub-GeV dark matter particle. And so here the idea is that dark matter is not a black hole, but it is a particle. And what can happen is that a particle dark matter can decay to 2 photons, or 2 particle dark matter can annihilate to give me 2 photons, right? And for the decay and the annihilation, the spectra can be given by this, where for the decay case, the tau is the lifetime of dark matter particle, m chi is the dark matter mass, and for the annihilation, the sigma v is basically annihilation cross section, rho is the density of dark matter, and again m chi is the mass, right? So given the mass, lifetime and cross section, you can again calculate the flux of photon coming from particle dark matter, and given the sensitivity of MeVCube, you can again see the reach of MeVCube, and these are the results. So the left hand side plot is for the decaying dark matter, where in the x-axis is the mass of dark matter particle in MeV, y-axis is the lifetime, and again the solid lines are showing the reach of this MeVCube, right, depending on the size that is launched. And you can see that previous limits are these lines, anything below is ruled out. So you can see again that with the launch of MeVCube, you can reach new regions of parameter space. The same is true for annihilating dark matter, where again in the right hand side plot in the x-axis is the mass of dark matter particle, y-axis is the annihilation cross section, and again the solid lines are showing that you can reach new regions of parameter space with MeVCube, right? So the essential point here is that with a small scale detector like this, with low cost and less time in development, you can actually do great science for dark matter physics, and potentially it can discover dark matter. So to conclude, we are seeing that MEV gap is a limitation for both gamma ray astronomy and also for dark matter search, and MeVCube is built on the CubeSat technology that will try to explore the MEV gap. And what I've shown is that with the current sensitivity, it can reach new regions of parameter space for dark matter, both evaporating primordial black hole dark matter, decaying and annihilating dark matter particle. And in future, if it operates, then it can constrain new regions of parameter space or potentially discover dark matter. So thank you.
Thank you for this great talk. So, why this MEV range is not explored that much? Is there a lot of background corresponding to that?
Yes, so let's go back. Yeah, so there are many reasons for that. So one big reason, as I said, there has not been any sort of dedicated mission that was launched after COMTEL. But if you look at the proposed telescopes and their sensitivities, they're actually much better. So this MEV gap will not be there. But what you said is also true, that in this range, we actually expect a very large amount of background, right? And most of the backgrounds are actually coming from either cosmic rays, or you can have some diffuse extragalactic background. And also sometimes the materials in the telescope can get activated by cosmic rays. So there are many different backgrounds that people take into account. For background, I can show you something, which is, yeah, okay, so this is a sort of slide that I've stolen from the COSI collaboration. But the idea is that this is the background that they expect in the energy, in the x-axis, y-axis the flux, and these are all the different backgrounds that they have taken into account, right? So there is a large amount of background that you have to subtract for your sort of thing to do.
Thank you. Thank you.
Thanks for the nice talk. So I have a doubt regarding you said that you can explore the new parameter space. How much right you can go, like in mass
yes.
of PBS?
So that is actually determined by the range of energy that is of interest, right? So let me go back here. So you see the energy range of interest is like 200 keV to 4 MeV, right? So wherever this is actually working, you can probe, obviously, for your particle dark matter candidate PBH dark matter. But if your photon flux is outside somewhere.
But right now, a PBH that would be evaporating is set by the evaporation mechanism. For instance, if we take Hawking evaporation, so it sets up a mass scale which would be evaporating right now, and you can expect to detect that. Right?
Yes.
So you can't go to the right up to a certain point.
No. So the point being, okay, let me go back to the plot. So there are two things. First of all, you see the mass range here that I'm interested in, like. So for example, the temperature that I will get from this mass of primordial black hole, it should fall bang on in the range of interest for this MeVCube, right? And the second thing that you're saying is correct, that you can't go to right because you're seeing the limits are going bad, right? So one thing obviously is the effective area can act, but the most important part here is that as I'm increasing the mass, the rate of evaporation is dropping, right? So with Hawking evaporation, you don't, like, the rate is very low. So the flux you will not be able to see in a given time.
Okay. And just one comment.
Yeah.
So if we consider the modified mechanism like Dwali, what Dwali has proposed, so I believe this MeVCube can even detect some of the. So they can't.
Okay. So the problem with this Dwali proposal is that it says that at very light masses, like 10⁹ grams or so, you will sort of slow down the evaporation. But then again, if you calculate the temperature for those black holes, that is much higher. It's beyond the capability of MeVCube, right?
Oh,
so you have to sort of stay in their energy range.
I see. Okay, thanks.
Yeah.
So I have a question. So can you show me the flux, that background and
yes.
No, not this one. I think where you showed the PBH.
The PBH, yeah. Yes.
Yeah. So what's the like signal by background ratio? Like that's the background, right? What I understand.
Yes.
So.
Okay, so that will be determined by, first of all, the sort of background is fixed, and that is determined by some analytical forms that people have fitted with the COMTEL data and also the cosmic X-ray background data. And then you have to determine what is the signal, and that will depend on the mass of the primordial black hole and the FPBH, right? So
yeah, so that's the signal profile, right? And you have a background. But I am more worried about the systematic uncertainty of background. So how do you actually estimate the significance?
Yes, so the idea here is that, so one way that people try to do this is that you take, yes, so you see this is the sensitivity of MeVCube, right? So what you do, a simple exercise is that you just say that my flux from the new signal should be within this thing, right? So this is a very naive way, but what I have tried to do is that because right now the analytical forms of backgrounds are coming from COMTEL fits, right? Mm-hmm. And when the MeVCube is up, its result may differ from the COMTEL, right? So then what I did is, for the limits, is that I did a Fisher forecasting where I have background and I have signal, and I have, for the signal, I have marginalized over all the background, and I have tried to see the error bar that will be achieved using MeVCube, right? So I have taken into account the uncertainties that will be achieved with the co-emission.
But have you taken any
MeVCube.
systematic uncertainty in the calculation?
Like what kind of sensitivity? Like the instrument you are saying, right?
No, even in the background fitting, there should be some systematic uncertainty, right?
Correct. So yes.
Yeah. Have you taken that?
Yeah. So I have varied all the different so for background, I can show you something. Yeah, so this is the total background model that I have taken into account. So this is something that people have been taking into account. So this is the galactic contribution, this is the extragalactic contribution. This is obviously a fit to some data from COMTEL and all. And in my analysis, I have varied all these parameters, right? So we don't know their values because we have not detected using the MeVCube, right? So I have actually marginalized over all these parameters to get the limits.
Okay, thanks.
So my question is, what is the detection technology of this MeVCube? How is it detecting the gamma rays?
Yes. So the idea being that yes. So this one, these are the semiconductor detectors, right? And this is not a single cadmium zinc telluride, right? You see there are these small cubes, right? So these are all individual semiconductors, and what you have is that in each individual site you have actually a readout. So if you have scattering at any site, you can get the sort of signal in the readout, right? And the first layer is actually taken for the sort of scattering, Compton scattering. The second one is used for the absorption, right? So the claim is that with COMTEL you couldn't have detected these electrons in the first layer because they didn't have individual sort of readouts. But with this telescope, you can get a better angular resolution and energy resolution because you try to detect both these electrons and the absorbed photons.
Also, does it have would it have pointing capabilities? For example, you want to look at dark matter from dwarf galaxies, right? So can it point towards that, or is that technology not available in this format?
Okay, so the main idea here is that these telescopes these are not built for dark matter, obviously. They don't sit and talk that we will make a dark matter instrument. But their main goals, if I've shown you, are this gamma ray burst and all, right? So they must have a pointing sensitivity, right? So the idea here is that they are more sensitive to lines rather than a continuum. Because if you try to start to look at the continuum and look at various parts of the sky, the backgrounds will kick in, and that will sort of kill their sort of main idea, right? So these are actually, that's why these limits from this dark matter decay and annihilation, which will give lines of photons, that are really good, right? But if you look at this PBH and all, these are not that great. And one reason is because it is very good sensitive to lines rather than the continuum.
Thank you.
Yeah, so this is actually a group from DESI, and what I have read about them is that they have, with the material in use, cadmium zinc telluride, they have made tests, right? So what they do, they calibrate the system with some known sources, right? And all the results that you see here, these are done after simulation and also testing, right? So this is the point that I am aware of. Recently, I don't know what is the stage, but at some point I will try to contact them also.
So how do you distinguish between the different photons and different electrons if more than one photon is hitting my first surface?
Yes, so the idea is, one point here is that this is actually, with one photon you cannot do directionality, right? The point is, you can see in this picture, right? Anywhere from this cone your photon drops, you will see a signal, right? Just the same signal, right? So then the point is how many photons you detect becomes important, right? And I don't have that picture, but what will essentially happen is that you will get many such cones, and the intersection of all these cones will give you the directionality.
Sorry, I asked if there is more than one photon that
Yes.
is being incident on the first surface,
Yes.
then I'll have two outgoing electrons and two outgoing photons.
Correct.
How do you map one to the other?
I think for a source you need more photons from a single direction to point it back, but if different photons come in at same time, then I don't think it's sort of very good to, it will take it as a background, I think.
Sorry, my question was, you are calculating the energy of the initial photon from the scattering process, from the Compton scattering, right? By back calculating it.
Yes.
So if the second surface detects two electrons,
Yes.
how
Not
will it
first
know?
surface. First surface detects electrons. Yeah, so this is not a single crystal, so they have individual pointing. So X, Y are different. So you can get X, Y, Z with this direction.
Okay, thank you.